Okay, let's make another video because we can, and I've got some time. Let's see. In some previous videos, we've tried to answer whether or not the moon was moving towards planet Earth or moving away from it. Then we went more generic. What about just planets orbiting stars? Are they moving towards a star or away from it? Then pushing it like even further, we went like, okay, what if we have an exoplanet? An exoplanet somewhere in the big wide universe circling some type of star out there. Can we somehow calculate the mass of the host star if we know the distance between the exoplanet and the host star and the period? So how long does it take the planet to actually make one orbit around the host star? And of course, like, you can calculate all that stuff. In this video, we're going to replace the host star by a black hole. Because black holes are cool. Yeah. And we're going to, again, do some calculations because it's fun. It's fun to calculate. So, let's introduce some black hole into the equations. Why? Because we can. Yeah. So we did calculate whether or not the moon was moving towards Earth or away from it. That actually started all these videos because Google couldn't make up its mind. We calculated the mass of the star Gliese 581 based on the exoplanetary data of one of its planets known as Gliese 581d. And what if we replace our sun by a black hole? A black hole with quite some appetite. Would the physics be different? That's the bird behind me, okay, in the garden. So, we have these two equations from the previous videos. So a cubed over p squared equals gm central star divided by 4 pi squared. And the period equals 2 pi a over the velocity. Yeah? So you remember those equations? So let's make the central star a black hole. So basically we're just replacing this thing, the mass of the central star. Let's replace it with the mass of some black hole. Yeah, because basically a black hole is just a star that's collapsed on itself. It's a bit like a grape that's turned into a raisin, just a lot smaller, but with the same mass. So it's like a grape that that turned into a raisin without losing all its yummy juices. Okay. So we've got this equation: a cubed over p squared equals gm black hole divided by 4 pi squared. Now, if we only know the circumference of our orbit c, and we use a capital C here because the lowercase c is normally used for the speed of light, and the period of our orbit is a capital P. So then what's the mass of our black hole? So we only know like our circumference, and we know like how long it takes to make one orbit. That's the only data we have. So let's assume, for now, c is 25 million kilometers. I'm going to write it down, 25 million kilometers. And p is like 30 minutes. So I'm just writing it down on a piece of paper because we need it again at some stage. So, this is our equation. Yeah, so this is our equation. A cubed over p squared equals gm black hole over 4 pi squared. Yeah. And also realize that the circumference of a circle, if it's a pure circular orbit, which of course, like in reality it isn't, but hey, say I mean, we can approximate values. So if c is 2 pi times the radius, then we don't use r here, we use a. And a being the distance between the black hole and the planet like orbiting it. Yeah. But what if c equals 2 pi a? Then how big is a? So if c equals 2 pi times a, then how big is a? Well, a is c over 2 pi. But how do I know that stuff? Well, this is how I've learned it in school. I call it the triangle trick. So you draw a small triangle. This is a c. C equals something. That something is always below the line here. So this is the line. Below the line you have like 2 pi times a. Now if c equals 2 pi times a, then 2 pi equals c over, that's why I've got the line here, a. And a equals c, the circumference, over, again, the line, 2 pi. So it's quite easy. It's quite easy to actually answer that question. Eh? If a equals b times c, then how big is b and how big is c? That's basically the trick here. So I call it the triangle trick. So the only thing we're doing here is we're replacing this a over here. This a is substituted with this thing here, c over 2 pi. Yeah, so c over 2 pi to the power of 3 over p squared equals gm black hole over 4 pi squared. Yeah? Now, then you can actually use another trick. I call that the cross multiplication trick. If a over b equals c over d, then a times d must equal b times c. So then a times d, now there's supposed to be an equal sign here, so you think an equal sign here, okay, it's an equation, is a b times c. I call it the cross multiplication trick. So in other words, this whole thing, c over 2 pi to the power of 3 times 4 pi squared, that's this part, must equal p squared times gm black hole. Just cross multiply those parts. So we then move this whole, or we copy this whole equation to the next slide. So we're here. Now the only thing I'm doing here is like, I'm just calculating this. So c to the power of 3 is c times c times c. Well, it's still c to the power of 3. 2 pi to the power of 3, well, 2 times 2 times 2 is 8. That's the 8 here. And pi times pi times pi is pi to the third. Then I just I just multiply those two. I bring this part up here. Okay, so you have like 4 pi squared times c to the third over a pi to the third. Now 4 over 8 is the same as 1 over 2. Just simplify. That's why I've got a 2 here. You can think of 1 here if you want to. There's a 1 here, but there's a 2, definitely a 2 down here. Then pi times pi up here, and pi times pi times pi down here. There's only 1 pi left down here that you can actually eat. It's a yummy pi, okay? So it's c to the third over 2 pi must then equal p squared times gm black hole. Then I copy this whole formula down here. So this whole thing sits here, it's the same thing. And I start to divide both sides by p squared times g. So this whole thing over p squared times g, and that whole thing over p squared times g. But the p squared times g here and the p squared times g here, they cancel each other out. So the only thing that's left here is the mass of the black hole. You see that? Now this part is a bit tricky, this part. If you have like a over b divided by c, that's the same as saying a over b times 1 over c. That's just another trick you can, I mean, I don't have place for all the trick, I don't have enough space for all the, to show all the tricks here. That's just another trick you can use. So you're basically writing this part here, yeah, this part here goes there, and you start to multiply by the inverse of this one. So 1 over this one. Yeah, that's this one. So c cubed times 1 is simply c cubed, and 2 pi times p squared times g is simply 2 pi p squared times g. So now finally we've got an equation that allows us to calculate the mass of the black hole if we know the circumference and we know the period. Yeah, they're like the variables here. Now there's only one other issue we have, that if you actually Google the value for g, the gravitational constant, you normally find it in cubed meters over kilogram seconds squared. But our units are in kilometers, our units are in solar masses, and our units are in minutes. Now to go from meters to kilometers, just realize that like how many meters do you find in 1 cubed kilometer? You find 1 billion of them. That's so, yeah, like 1,000 by 1,000 by 1,000 meters creates 1 cubic kilometer. So our value, because we want to go from cubed meters to cubed kilometers, we need to multiply by 10 to the power of -9. Yeah, there's an incredible small amount of like cubed kilometers in 1 cubic meter. how many? 1 billionth. That's the answer. Of course, like, well, how many kilograms do you find in a solar mass? It's actually 2 times 10 to the power of 30. You can Google that. That's roughly the mass of our sun. Okay. And this one, going from minutes to seconds, well, you simply multiply by a number 60. So the G you find online. Okay, the G you find online is typically this number. That's a G you find online in cubed meters over kilograms per second squared. Our new G, if we multiply this G by 10 to the power of minus 9 times a solar mass, you get this new g, which is simply the same g in different units. And there's only one g, that's a unit, it's like the gravitational constant. It's a constant, so it's not changing. But here I'm just expressing g in different units. That's all I'm doing. Yeah? So let's try this in Excel. Let's try this in Excel. So what I'm going to do already, I'm going to copy this number, this whole thing here. So Control C it. I'll go into Excel. Select a cell somewhere. I'll do a paste special of some text because I don't want all the formats. I just go OK. Bang. So, what do I have? I have this part and this part. Now, let's first pick up the units. So I'm just going to Control Exit, cut it, and place it like somewhere there. And then this part, 10 to the power of 11 in Excel is simply E11. That's 10 to the power of 11. So that's our G. Okay, that's our G. Then our circumference, I wrote that down, remember, that was 25,123,123 kilometers. I said kilometers, not with all that other stuff, just kilometers. And our P was 30 minutes. That's in minutes. So we can now calculate the mass of the black hole. Black, not hole, black hole. And what I sometimes do, black, I can't even type, okay, black. What I sometimes do, I select all the text there. I go to my font setup, and I just make it subscript, because I think it looks a little bit better. There you go. Yeah. What's the formula again? I can't remember. This thing here. So what I'll do, I'll use my snipping tool. I'll go new snip. I'll just select this part. Whee! I do edit copy in snip, edit copy. I go back into Excel and just do a Control V. I paste it. It's a bit big, so I press my Shift key and I start to resize that formula. Click and drag. I can resize it even more. I press my Shift key, so it maintains the ratio, width and height. There you go. So the black hole mass equals what? Equals c to the power of 3. So that's this thing here to the power of 3. Remember, we've already put g in units of kilometers, so there's no more conversion needed here. Yeah, divided by opening bracket 2 times pi with the brackets times p. Now p is in minutes, so opening bracket. This is in minutes, so I need to multiply with 60. And take it to the power of 2. And finally multiply by our G. And then close the brackets again. Because I've started here with an opening bracket. So I need to end here with a closure bracket. Hit enter. So this is in units of solar masses. Yeah. Or maybe just solar. Units of solar mass. Maybe this. I don't know. Solar masses or solar mass. I'm not entirely sure. Okay. Now this one is in scientific number notation or scientific notation. If you just want to see this in number, you just change it here from scientific back into number. So you can see it's roughly 5,750 solar masses. So it's quite a nice big black hole. So aren't we supposed to be sucked into it? I mean, isn't that the whole idea of black holes? That like once you go in there, you disappear forever? You end up in like some different alternative universe? So what's happening here? So, I mean, this video is just showing you like how you can calculate the mass of a black hole based upon the period. So how long it takes you to make one orbit around the black hole. And what was the other one? The circumference. So the length of your trip around the black hole. Yeah. But it doesn't say anything about like whether or not you're actually within or outside of, for example, the event horizon. So we're going to talk about that one in the next video, okay? Have fun with this. Bye bye.